Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1770 Antoine Lavoisier Elements of Chemistry. The year is 1770, marking a pivotal juncture in the nascent science of chemistry, witnessed the emergence of Antoine Lavoisier's profound contributions, woven into the fabric of scientific thought before culminating in the landmark publication, Elements of Chemistry, later in 1789. A careful examination reveals a narrative of intellectual genesis, meticulous experimentation, efficacy, that indelibly shaped the course of scientific progress. The intellectual landscape preceding Lavoisier's work was itself a complex and often chaotic environment. Alchemy, though declining in its influence, still cast a long shadow, its practices and principles lingering in the minds of many practitioners. The phlogiston theory, championed by Georg Ernst Stahl and widely accepted, attempted to explain combustion, respiration, and calcination by positing the existence of phlogiston, a substance released during these processes. This theory, while internally consistent to those who embraced it, ultimately proved a significant obstacle to a proper understanding of chemical reactions. Preceding Lavoisier, chemists like Joseph Priestley and Carl Wilhelm Scheele diligently probed the properties of air and combustion, uncovering crucial clues would, in due course, inform Lavoisier's investigations. Priestley's discovery of dephlogisticated air, later recognized as oxygen, was particularly significant. The works of these predecessors, though often interpreted through the lens of phlogiston, provided the empirical foundations upon which Lavoisier would construct his own revolutionary framework. Scheele's meticulous observations on the composition of air and his studies of various acids and bases were likewise instrumental. Lavoisier's own investigations, commencing in the late 1760s, initially centered on the nature of combustion and calcination. His meticulous approach, characteristic of a modern scientist, set him apart. He issued qualitative observations for painstaking quantitative measurements, employing carefully crafted balances and precise apparatus. Lavoisier methodically tracked the mass changes occurring during chemical reactions, a crucial departure from the predominantly qualitative methods of his contemporaries. He began his experiments with the calcination of metals such as mercury, sulfur, and tin. He showed, through his meticulous balance, that metals gained weight when they calcined, and importantly, that this increase was proportionate to the amount of air consumed in the process. This observation directly challenged the phlogiston theory, which predicted a loss of weight as a metal released phlogiston during calcination. Lavoisier's experiments demanded a rigorous re-evaluation of combustion itself. He observed that a component of air, the very dephlogisticated air identified by Priestley, was essential for combustion, and that this component combined with the burning substance. Furthermore, he established that this same substance was necessary for respiration, suggesting a fundamental connection between combustion and animal physiology. He named this essential air oxygen, reflecting its acid-producing qualities, a naming decision that, while initially considered somewhat unfortunate, would later become a cornerstone of chemical nomenclature. His studies on the composition of water, showing it to be a compound of oxygen and hydrogen, similarly marked a significant shift in understanding. These crucial discoveries necessitated a fundamental restructuring of chemical theory. Elements of Chemistry, published in 1789, provided this framework. The book, structured with meticulous logical rigor, did more than simply describe chemical reactions. It laid down the principles of the conservation of mass, a fundamental law of chemistry, stating that mass, the quantity of matter, is neither created nor destroyed in a chemical reaction. Lavoisier presented a systematic nomenclature based on the composition of substances, introducing prefixes, suffixes, and descriptive names that facilitated clear and unambiguous communication. This was an enormous advancement. Before Lavoisier, chemical terminology was a chaotic patchwork of idiosyncratic terms. Lavoisier's systematization imposed order on this linguistic landscape. He organized the elements into a table and carefully described their properties. Again embracing quantitative methodology, his table of elements, though incomplete by modern standards, included substances such as oxygen, hydrogen, sulfur, and carbon, and served as a crucial model for later chemists. Lavoisier's approach emphasized precision, accuracy, and reproducibility, setting the stage for chemistry's transformation into a quantitative science. The immediate impact of Elements of Chemistry was considerable. It provided a coherent and internally consistent framework that superseded the phlogiston theory, Offering a more accurate explanation of chemical phenomena, it enabled chemists to understand chemical reactions and predict their outcomes, providing a foundation for advancements in areas such as industrial processes and pharmaceuticals. The precision offered in the work also fueled a surge in experimentation, although some, notably Priestley, clung to the phlogiston theory for several years. The evidence amassed by Lavoisier and his followers proved ultimately overwhelming. Lavoisier's theories spread quickly among the enlightened scientific community of his time, and his approach was swiftly adopted by younger chemists. The long-term influence of Lavoisier's work is profound. It laid the groundwork for the development of modern chemistry, influencing fields such as organic chemistry, biochemistry, and material science. The law of conservation of mass, championed within Elements, remains a foundational principle in all branches of science. Lavoisier's systematic nomenclature continues, with evolutions, to be used today. His quantitative experimental approach established a model for scientific inquiry. Additionally, his rigorous emphasis on clear communication and standardized terminology facilitated the rapid dissemination and advancement of scientific knowledge globally. His work indirectly motivated the development of the periodic table of elements later. Pursuit of understanding the structure of atoms. The contributions of other individuals were, of course, essential to Lavoisier's synthesis. The aforementioned work of Priestley, Scheele, and others, providing much of the empirical data, served as crucial building blocks. The collaboration with his wife, Marie-Anne Pierrette Pauls Lavoisier, was also of immense importance. Marie-Anne not only assisted in the laboratory but also skillfully translated scientific papers, created detailed illustrations of the experimental apparatus, and meticulously recorded the experimental data. Her contributions elevated the quality and comprehensiveness of Lavoisier's work. Antoine Fouqueray and Claude-Louis Berthollet also were influential chemists who were among the earliest converts to Lavoisier's scientific system, and their support helped in the dissemination of his ideas. Count Rumford's contributions to the understanding of heat and its nature influenced Lavoisier's later work in calorimetry, adding to the understanding of energy conservation. Critiques and revisions of Lavoisier's work emerged, of course, but they mostly served to refine and strengthen his framework. Some chemists initially resisted his ideas, clinging to the phlogiston theory, or simply hesitant to embrace a radical change. Others questioned certain aspects of his nomenclature or proposed modifications to his definitions. Some, for instance, debated the precise role of caloric, the substance hypothesized to carry heat. However, these critiques generally did not invalidate Lavoisier's central principles. They stimulated further research, leading to a deeper understanding of chemical phenomena. Subsequent generations refined and extended his theories, resulting, eventually, the periodic table allowed and conception of the tragic circumstances surrounding Lavoisier's demise, executed during the French Revolution, add a stark and unsettling chapter to the story. While his scientific contributions had a profound and lasting impact, the political context of the time demanded a severe price. Even though his contributions were of great value and his work had benefited society, the political climate of the French Revolution was immune to the value of scientific advancement. The irony, of course, in Lavoisier's application of scientific methods had, in a way, served to make chemistry a rigorous and systematic science, ironically creating an environment where science was more susceptible to the pressures of politics. In retrospect, Lavoisier's Elements of Chemistry served as more than merely a textbook. It provided a paradigm shift, transforming chemistry from alchemy and speculative theorizing into a modern, quantitative science. His work, a testament to the power of the scientific method, laid the foundations for the vast edifice of modern chemistry. It remains a landmark achievement, a reminder of the revolutionary potential of scientific inquiry and the profound consequences of intellectual courage. His legacy endures, not only in the textbooks and laboratories of chemists worldwide, but also in the very fabric of our understanding of the natural world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.